So, Stratis, can we start now?
Sure.
Yeah, okay. Good evening, everyone. On behalf of IIT Kanpur, I want to warmly welcome you all for the fourth day of PERA 21. The topic of today's session is solar integration in the United Kingdom and India, technical barriers and future directions. For delivering today's session, we are fortunate to have with us Dr. Stratis Batzelis. Dr. Stratis Batzelis is a lecturer with the School of Electronics and Computer Science, University of Southampton, United Kingdom. He has long experience in solar photovoltaic systems and is currently a research fellow of the Royal Academy of Engineering working on solar integration challenges in developing countries. Prior to this, he held an EU Marie Curie Fellowship at Imperial College London, United Kingdom, on more grid-friendly PV systems from 2017 to 2019, while he received his PhD degree from the National Technical University of Athens, Greece in 2016. Dr. Batzelis' research on PV system has received about 1.6 million pound funding, and his research work has been published in 37 journals and conference papers. He is a senior IEEE member and currently serves as an associate editor in IEEE Transactions on Sustainable Energy. His research interests involve integration of renewable and distributed energy resources, especially solar photovoltaics and inverter-based generation, power converters control, and power system stability. So with this, I would like to hand over the screen to Dr. Batzelis and request him to deliver today's session. Thank you.
Thank you very much, Arindam, for this kind introduction. Let me start sharing my screen first. Is everything fine? Can you see my screen?
Yeah, it's fine.
Yeah. Okay, so first of all, I would like to congratulate the IEEE PES groups in IIT Kanpur and Uttar Pradesh. It's a quite innovative and very, very good initiative that I know that you keep having. So congrats for that. And yeah, thank you for having me today. So I know that this PERA 2021 is focused mainly on microgrids. But what I wanted to talk to you about today is really this, the results we had from this white paper we co-developed with our Indian partners that refers to solar integration, how we can have more solar into the power system. And even though it is tailored around the power system itself, because many of these challenges come from, we have seen them already in microgrids, because everything started from a miniature of the power system, which is the microgrid indeed. I think that it is highly relevant for all these people that would like to see what happens when you have either a small or a large power system, and when it gets full of renewables and solar, what are all these challenges that you're facing, how we can overcome. So yeah, let's start with the main part of the discussion then. That should be come here or something. Okay, so a few words about the motivation. I mean, we are all well aware of the tremendous increase of solar integration worldwide, and we can see that still it's a polynomial increase or maybe exponential. But if you take a better look, you'll see that the places where they used to live, like in Europe, they have started showing signs of stagnation. Okay, so we know that solar keeps increasing worldwide, but there are many countries that they think that they have been there's a limit to those. So we would like to see holistically what are all these technical reasons that can do that, because there are lots of financial reasons, policy reasons, okay, and we could not address all of these in one paper, but we would like to see technically what's that acts as a barrier, as a limitation. And we wanted also to see how this differs between the UK and India, which were the two case studies. So that was the purpose of this white paper. It got published in April 2021, and it is freely available. So anyone that would like to see more about this work, they can visit this website. I also have a link at the end of the presentation to learn more about this work. But first, just a few words about the framework that this was developed. So this was part of a UK-Indian joint virtual clean energy center. It's really a 5 years consortium that involves 10 universities from the UK and India, which have been classified into 3 consortia here. And of course, IIT Kanpur is part of this collaboration. So this hub has attracted about 10 million funding from the 2 main funding authorities in the two countries. And we are focusing mainly in clean energy, and solar is a big component of that clean energy, by the way, energy storage and network technologies. So that is the scene, and let's start with the main part of the presentation now. So what I'm going to be talking to you today is first a few words about what's the solar picture today in the two countries, and then I will start outlining the technical barriers we see that exist against a very high integration of solar in particular. And afterwards, we're going to be outline the roadmap that we have envisioned on how we can reach a high solar power system in the future. The solar picture today, well, honestly speaking, this was what happened in April. Okay, so it's a few months old, but still a bit valid. So at that time, we had about 630 gigawatts of solar globally, which is a quite big number. But of course, the integration levels and trajectory change a lot among the countries. In the UK, what we would like to say is a stagnated market, because you can see that you had a very high increase in the previous years, early in the previous decade, but now it has stagnated. It kind of has converged to a particular point, which is a little bit less than 14 gigawatts of solar. And even though this is a good number, it's 17% integration in terms of capacity, we know that this has happened mainly because of the closure of feed-in tariff schemes. So that was mainly a, let's say, policy-related reason. But all these policies come from the technical stuff. So the question here is why we couldn't install any more solar. And I mean, we installed so much solar at a time when it was more expensive. And in the UK, that doesn't have too much sunshine. Okay, so why we have stopped now? We have recorded almost 30% peak generation, and a national grid estimates that can reach up to 66 gigawatt, which is like 4 times that by 2050. But we need to do many, many things I'm going to be discussing later on. So that's what's happening in the UK. In India, we call it an emerging market still, because we still are in decrease of integration. And so things are going quite well, but we need to see that the reality that we are far off the 100 gigawatt target that was set by the government. And so, I mean, last time we checked, it was a little bit around 40 gigawatts of solar. I expect now to be a little bit more, which was 10% integration in terms of capacity, not bad at all. But actually, what we've done in India is we have installed a lot of utility scale solar, which is, let's say, the easiest part to do. We have not made too much progress on the rooftop solar and generally the distributed version in small systems, because there we had only 6 out of 40 gigawatts. And the early signs that we've observed is that there are concerns in the solar hosting capacity, mainly in rural areas where the network is not adequate to do that. So this is the situation as it is now. We have stagnation in the UK, we have good development in India, but still early signs of stagnation, especially when it comes to rooftop. And I also would like to mention in this slide what's happening from the market perspective, even though this is not the focus of the paper, just to put you into the picture. What's happening is we all know that the renewables are getting cheaper and cheaper. And this is the latest report of IRENA, where it has the levelized cost of electricity of 4 very popular technologies. The important thing here is that solar photovoltaics are becoming the cheapest ever. They are expected to reach this year about 4 US cents. As a global value, it's not the lowest that we can have. It will be cheapest even than onshore wind. And it's forecasting to be cheaper even than operating some outdated coal mines. So it's becoming very cheap. It's not only environmentally friendly and trendy, if I'm allowed to say, it's becoming cheap. So there is another reason that we really want to have more of it. So we need to figure out if there are any difficulties what we need to do to allow it more. And I would also like to mention here this post-COVID recovery plan that many countries worldwide have put forward. The UK is leading that, and also the European Union with the Green Deal. Recently, the United States of America joined. So things are going towards this trajectory. Lots of renewables. And the last thing I wanted to mention here is the transformation of the electricity market. So I realize that many of us may not be very familiar with all these terms, but I selected this diagram here, which shows graphically how the money we spend essentially for the electricity are kind of categorized in different types. So what happens now is the big chunk of money is the energy produced, the kilowatt hour, the megawatt hour. This really corresponds to the fuel that at the moment we mainly need to spend to produce electricity, right? And there are some supporting markets like capacity and ancillary services. So all these things change very rapidly, depending on the country, of course. And by 2030, we expect to have something like this. We expect to have the electric energy market itself be shrinked because we will be having renewables that have near zero operational cost. Okay, we don't need to burn either sun or wind when operating this infrastructure. So the energy cost itself is going to be lowered, and we have seen that. But other parts of supporting markets, if I may say, are going to increase proportionally. It's really, what we need to keep having there so that everything can run smoothly. So we have all this, transformation in the financial sector happening, which really is the further motivation to see whatever technical barriers we keep facing integrating these renewables, mainly solar here. We need to understand them better and act properly, because it will be financial incentive apart from all the other things we keep discussing in the past 2 decades. So this white paper has mainly 2 big chapters. One has to do with technical barriers, and the other one is the roadmap. So now I'm going to be talking about the technical barriers, and I have some figures here selected which give the big picture. I will try not to go too deep into the technical details because I have a limitation in time, but just to give you an idea. Here, this diagram tries to relate how some of the inherent characteristics, and in this case, limitations of solar technology, relate to emerging challenges of the power system and how these all are manifested to barriers, essentially towards high integration. For example, we know that solar is variable and uncertain. Okay, you can't have it during the night. Even during the day, you may have clouds passing by, so the generation is intermittent. So this is a big burden in terms of balancing the power system, because you need to have some other sources there online to cover the gap that solar leaves. Or at the same time, you can see that this is related to voltage issues, because you have the PV plants installed in a distributed manner in medium voltage networks and low voltage. So when you have intermittent generation there, this reflects to intermittent power flows that that give rise to voltage issues, either increases or decreases. So it makes it more difficult. Another example is the fact that the energy, the solar system does not have any inherent energy storage. It doesn't have any rotating masses. It doesn't have anything like that. So no batteries. So the problem here is that, therefore, it cannot contribute to the balancing market. It's not like you can time shift some of the sun radiation during the night. No, you cannot do that on its own. But it also contributes to what also we see as an emerging challenge in the power system, which is the falling of the system inertia. I'm going to talk about that later in more detail. But the important thing here is that when we replacing signal generation with solar systems, we see that we contribute to the falling of system inertia, and this itself is related to a myriad of stability issues. And another example I would like to mention here in this diagram is the power electronics interface. Solar systems interface the grid through inverters, much as like many other renewables, and distribute energy resources like electric vehicles. So the inverters have lots of advantages over machines, but they have also disadvantages. And the major one being cannot provide current more than the rated number a lot of time. And so this overcurrent limitation actually contributes to the short circuit level reduction we see in regional grids. And reduced short circuit level means that we keep having stability issues, and also the protection schemes we keep having do not work that effectively. So you can see it's like a big mess, to be honest, a very complicated situation. I'm trying to say a few words in more detail now about the most major ones. But the big point here is that all these are interconnected, and we need to see what we can do to address each of these challenges. And there are many actions, some of which address many challenges at the same time. So a few words about the balancing and flexibility challenges. This really means whether the fact that we're not able to dispatch solar whenever we want it, because it's not up to us. These are some transmission demand graphs provided by National Grid and some estimations. And you can see that in various scenarios, the net demand in the transmission system may be affected a lot by increased solar generation. This is quite similar to what in the United States called duck chart, because it looks like a duck if you think about it. But the whole point here is that during the node, we may be having a low peak in demand because of the increased embedded solar generation, which someone may think it was good, but no, it's not really a good thing. It's a bad thing, because at that time you need to have it's difficult to have some online generation to cover this gap if something gets lost, like clouds passing by or whatever. And also the retracting of solar then is quite fast. It happens at a fast rate, so you need to have some sources that are adequately equipped to support these high ramping needs. And this has to do mainly with balancing, but there's also the flexibility aspect, which relates mainly to the ramping capability that we have. And again, as we said, because solar is not very much guaranteed and dispatchable, we need to have someone else to pick up any deviations in the generation. This diagram here shows, this is a kind of a histogram, and shows the residual ramping capability you have in the UK 2021. So positive values means whether what is the rate of power that you can increase, and this is what you can decrease. And the two colors correspond to summer and winter. The important message here is that during the summer, as you can see, these curves are more reduced, which means because you have lots of solar at that time, you do not have too much other generation online to pick up any deviations generation, which means that you have reduced ramping capability. You can see this is lower and this is lower than the corresponding color. So this is like a reformation of what we said previously about this extra balancing flexibility challenges. And a few words about the power system stability now. Here I'm referring mainly to the system inertia, which system inertia technically is the collective inertia you get from all the rotating masses you have in machines and generators throughout the network, and act as a safeguard against the grid frequency. So you can see in this graph here, this plot, for different levels of inertia. Blue means little inertia. When you have a power imbalance in the network, like loss of generation, for example, then you have a drop in frequency, and the less the inertia, the more severe is the drop. And this is not a good thing. That's not a good thing, because when the frequency goes too low, some equipment cannot operate, especially the synchronized one, the ones that have machines, and needs to get disconnected. If it gets disconnected, it will lead to a domino-like effect with lots and lots of generation losses. So we don't want that. So we don't want low inertia. The problem here with solar is that it does not have any inherent inertia, because it doesn't have any rotating masses. So it doesn't have any energy storage inherent. So this is why this becomes a problem of solar. If you substitute, if you replace signal generation with solar, you lose out from inertia. This is another graph which I found interesting. This is a histogram again that shows the system inertia in the United Kingdom during entire year, and you can see the most common value of system inertia was about 220 GVA second in 2016-17, and it's forecasted to be lowered a little bit less than half actually in the coming years. So this is a validation of what we actually fear, that the system inertia is being reduced. It's quite common to have little inertia there, so more severe frequency fluctuations, and this is a concern for the system operators. And a little bit now about the short circuit level, or the grid strength, if you can say that. So this really corresponds to how the voltage behaves in the network during a fault. When you have high grid strength, then you have a fault, it's going to be reduced, but then it's going to be restored quite quickly and smoothly. You have low short circuit level, then you have a more extended time of oscillations to happen, and you have very low, and you have also some undamped modes. You may have also instability. So we don't want that. Generally, we don't want that. And again, we keep seeing in countries that have a lot of inverter-based localized generation, we can see that this is dropping. In the UK, you expect that in 2025, we're going to have on average 50% less social good level on average than what we had 1 year ago. So it's not a good thing. And I would like to end this particular description with what happened in the power cut of 9 August 2019 in the UK. That was about 2 years ago. This is the frequency actually plot of a disturbance. Many things happened. We had 2 simultaneously faults in 2 big generators, and this is why we faced these challenges. Eventually, it led to load shedding that had a great impact into many consumers, hospitals, and the railroad network. What I would like to mention here is that one of the reasons that this happened, that contributed, it was an offshore wind farm in Hornsea that was connected to the east side of England. And close to that point of the interconnection, there was a transmission network, and they had a lightning strike, and that lightning strike opened one of the circuits. So essentially what happened is it created a disturbance and a weak grid condition to that wind farm. It's not like it went isolated or something. The connection became weak, became low social good level, and you had a disturbance. And the control actually started oscillating, and as a result, it reduced its output by a very high number, like 80%, 90%. So it's like almost like a trip. And that was a substantial reason why we led to the situation. And also, during that difficult times, because the frequency varied a lot, we had some loss of mains on embedded generation. And embedded generation involved some solar parks and other inverter-based resources. So these have some protection against phase jump and against high rock-off, high frequency change. And this triggered, and as a result, they tripped as well, and they intensified the phenomenon. Okay, so this shows that this is another challenge when it comes to protection of these systems. And we faced these things in the UK, which is supposed to be a very well-developed power system. So this is why it's a concern. Let me, though, move on. The protection challenges. So the low circuit level affects how the protections in the transmission system work, which are quite complicated. But they affect also what happens in the distribution network. There, the protection is a little bit more simple, and in most cases, they're overcurrent relays. So I decided to have an example here just to give you an idea. Let's say you have a fault at this point, and if you have a local generation of PV here, the fault current that follows through this relay would be less than what it would be if this wasn't here. And you may have the opposite in this case. So the take-home message here is that tuning and the protection settings of these relays, it may not be very straightforward because you may have more or less current during faults I wouldn't expect. So it's more difficult. So we may need to change the way we of the protection system in distribution networks. So this really is very similar to what happens in microgrids, where you just overcurrent relays is very, very challenging if you want to have that. Usually you have more than that in microgrids. So this is what I'm saying, that the distribution networks start assimilating microgrid properties, you may say, with high integration of solar and other renewables. And also keep having challenges in terms of fault drive-through, which is fault drive-through means when the system is required to remain connected to the power system during disturbances. Here, this is an example of the Blue Cat fire that happened a few years ago in California, in the United States. So these things have been overcome somewhat, but we keep having disconnection of solar plants. So this is why I'm referring to that. I'm not getting into details, but the idea here is that there was a disturbance with a big fire, and about 40% of solar you can see disconnected, and then it just did not reconnect immediately. It took some time for some of it to connect, and then you have some PLL oscillations and instabilities, and it took some more time, and eventually even some of it did not connect at all until the next day. So it's important. We need to keep to have the solar as a reliable source in the network, because otherwise we cannot say that it can replace coal-based and fuel-based generation. Voltage issues. So the fact with the voltage issues, the main problem here doesn't have to do with solar itself and the nature of generation. It has to do with being localized. They have to do with the fact that we have generation in parts of the network that we didn't use to have generation. And this makes things more challenging. Makes it more challenging to have a voltage control that keeps the voltage always within limits, gives rise to reverse power flow. You have power flowing through directions that you didn't have in the past. And even though generally our circuits are bidirectional, you may have on-load tap changers that have different power ratings in the two directions. And there are other equipments that may not operate as you would expect. So this is also an issue, especially in this distribution network. And some remaining challenges, power quality. So in power quality here, we have distinguished between the voltage levels that we described previously. And with power quality, we refer here to harmonics and voltage unbalanced, really. So what I would like to say about harmonics is still this is a minor issue when it comes to the big power system. But this is a minor because we have a little integration. What we saw from a case study that took place in the UK, we took measurements from about 30 houses that had solar and energy energy storage, and they were injecting power to the grid. Is when we calculated the current total harmonic distortion with respect to the actual current, the fundamental of the current at that time, it was quite high. So this is not a conventional THD where you calculate the harmonic distortion over the nominal current. We calculate it over the actual current at that time. Okay. So when you have little generation at that time, the harmonic proportion of that little generation was quite high. It was 30% or 40%, tremendously high. So the point here is that even though in terms of network, this was not a big chunk, it is not a big chunk because we had little solar as a capacity, as in the solar hosting capacity at that point. Because if we didn't have that, and if all the generation was of solar, then this particular percentage would be quite a thing. Okay, and other things I would like to mention here is the variability of solar irradiance means it makes it more difficult to keep proper data and to have accurate forecasting. And also the grid codes and ancillary services. This is a very important vehicle and tool on how actually we can integrate these resources. And the big challenge here is really to strike a balance between having a reliable grid and keeping the motivation of the investment high. Because if you make a very stringent, a very strict grid code, you may think you're reliable, but just people and investors are not going to install any solar and any renewables if they have to, if it is very difficult and very disincentivized. Okay, so you need really to strike a balance here between reliability and motivation to install this. Okay, and this last slide here in terms of challenges refers to something which is not strictly related to solar itself, because it has to do with energy storage and lithium batteries in particular. But because we've seen, and as you will see later, that energy storage is a viable component in our decarbonization and high levels of renewables, we thought to include also what are the challenges this particular technology face. So I will not get into details of anyone can read in the white paper, but the idea is we're looking at the degradation of the lithium batteries that are facing and some balancing issues that they're having when you have many cells of the batteries connected in series and in parallel. And there are also other barriers with technology. High temperatures, operating temperatures, especially in some parts in India, that is also a barrier against the technology, and also other things which are not strictly technical, but we need to keep them in mind when we envision high levels of integration in the power system. Okay, so this is really a summary where we're trying to refer to common challenges in the UK and India, the two countries, and what is particularly important in the UK and in India, and how these relate to the big barriers or challenges I mentioned previously: balancing, stability, voltage, etc. For example, the fact of overgeneration of solar at midday is something that we expect to be having everywhere, really, because it has to do really with solar generation itself. In the UK in particular, we are more concerned with an increasing electricity mix, not only from solar, but also wind and electric vehicles, because this is what is going to be the big mix in the UK in the coming years. And also have famously volatile weather in the UK. So this makes the prediction and generation of renewables even more challenging. In India, In particular, we see that the grid code actually develops at the time, and ancillary services are developing following other countries, but still there is more work to do. And also at the moment, what happens is you have a lot of coal in the generation mixture, which is somewhat inflexible, and it is more difficult and more expensive to make these coal units to support high wrapping rates. And maybe another way maybe to integrate other generators of other nature as well. Another example here in terms of stability is the lower associated level is something that we expect to see generally. And in the UK in particular, we are mainly concerned in North Scotland, which is the northwest part of the Great Britain, where you have lots of onshore wind farms, and you may have also some offshore wind farms in the east coast of England generally. So there will be a concern, and National Grid is concerned whether we have PLL instabilities by 2030. But also have started seeing a high increase of falling of the power system inertia. So that's also a concern. In India, I wouldn't say that inertia is an issue yet. It is not at the time, but it's something that we expect that in the future possibly could be. We are mainly concerned of the low regional grid strength, essentially, in some isolated areas. The infrastructure is not very strong, so how would it be possible to integrate the distribution network solar plants there? It's quite a challenge. And there are many things, but I don't want to get, let's move on to the next section, which is the roadmap for high solar grid. So this chapter here, we try to outline, based on our ideas and our expertise, what we should do really to address or mitigate to some extent these challenges. And we have come up with 4 major directions that involve many things. And I'm going to talk about them later. But if someone would like to keep a few keywords or buzzwords in their mind, I would say more flexibility in the power system, and then higher demand side management and energy storage, very important things. And then 2 other things that relates to more grid-friendly PV systems, which is make them to provide ancillary services and operate in grid forming mode, which is something I'm going to talk about later. Okay, so the first direction, which we christened as rethinking the power system operation. This involves many things which are somewhat known in the industry. It's not like a big something different, but they're very important though. They're very important and refer to integrating many types of renewables, and it really refers to how the power system transitions, is transitioning now for the coming decarbonized decades. So we need more flexible generation, and we're going to have also coupling with different energy vectors. We need to have improved scheduling, so more frequent scheduling and dispatch, and better visibility to either to embedded generations like solar. And this aligns well with improved solar forecasting, because when you really know in better accuracy what we're going to have in a few coming hours, then you are able to dispatch more efficiently your generation. I also mentioned about grid codes and standards, and I would like here to focus mainly in this word, the harmonized word, because we have ended up every country having their own codes, their own standards, and it's very difficult for the industry to follow up, because they need to provide inverters, for example, that comply with all the standards and grid codes, and it's a big mess, and this really costs money to the industry. So a harmonization of the grid codes would be very effective in lowering the costs really of the technology. We need to keep that in mind. We also talked about the voltage control challenges in the distribution network. So there are some advanced improved voltage control optimization methods, which can allow keeping the voltage within limits without curtailing renewables. And this new concept of transmission and distribution system cooperation, so really not having these 2 systems as separate and independent, but communicating, coordinating, and exchanging powers both ways. And last but not least, a rethinking of the protection, especially in the distribution network, I think will be mandatory, because what we have now probably will not work in the future. So we need to see how we can change that and adapt it to be efficient in the coming years and decades. Okay, so that was direction 1. Now, direction 2, this is a demand response This is really a key technology that we think that will be very important in accommodating solar and other renewables, and this is why we have a special mention for it. It relates a lot with the major, let's say, limitation of solar, which is the variability. It's not dispatchable. You can have it when you want. So one thing is to have energy storage, that I'm going to talk about it later. And the other thing is also to see to what extent we can change our demand response as consumers, as industries, and everything. And this particular direction is very highly coupled with the multi-energy concept, having different energy vectors in terms of generation and loads, because it can be very effective this way. When you have air conditioning or space heating or electric vehicles, all these things, even though they are loads, and some of those have different energy vectors, so it's not strictly electricity, there are uses, of coolth, of heat. All these loads actually have a great deal of time shifting property. You can cool a space now and maybe after a few hours, and the temperature is going to be within an affordable range. So it's a very good actually combination here, which again is not a new thing. We're just reiterating that we need that. There has been some progress in some countries, including the UK. We have now one electricity company that provides dynamic pricing to smaller consumers. Even myself, if I wanted to have an electric vehicle and I wanted to charge it, in my home using this dynamic pricing, I could do that, which is very good. But still, there is a great potential here that we have not unlocked. And I think that India also is lagging behind on this particular aspect more than in the UK. So this is a demand response. And let's talk a little bit about energy storage now. Energy storage is, all these types of technologies you may have that can provide short-term, mid-term, or long-term energy storage. In the UK, we have pumped hydro as the largest version of it, and there is potential for compressed air storage, a great deal of potential, but it has been unexploited so far. And then you come to the batteries. Okay, you have the mobile version of the batteries, which is the electric vehicles, and we could expect to have a high uptake in the near future with recent commitments by the UK government. Whereas in India, you have a little bit about the 6 gigawatts of pumped hydro storage, and it's quite similar in the sense that also there is a big target of electrifying the vehicles by 2030 to 30%, which is a big number. So here the key message is you have different technologies, and you have also different needs. Energy storage has different applications in the grid. You may have frequency regulation or demand charge and response. You may have time of use shifting or energy arbitrage. And you can see that based on each application, there are different needs in terms of, for example, power to energy ratio. In frequency regulation, you really need a lot of power to be delivered quickly. But in time of use shifting, you really need the energy really not provided too quickly, if I say, not too at a high rate. And also the response time changes. So you have different applications with different needs, and we expect to have a mixture of different technologies here. But what I would like to mention here is among the energy storage technologies, batteries have a very big advantage now that they are the most modular and flexible, because for pumped hydro and compressed air storage, you are of course restricted by the geographical limitations of the area. You either have or you don't have the conditions to build it. Okay, but the batteries have the advantage that you can make them wherever you want, and especially when it comes to solar plants, they combine very well, because we have a case study in detail in the white paper, and we saw that it is financially also beneficial to install some batteries within the solar plant, because they use similar equipment. They will use the same feed-in inverter, they will use the same transformer. So there's a great deal of infrastructure which will be shared among the solar part and the battery part, and this will make it more efficient, more effective, and at the same time, it's going to increase the value of solar generation, because it will give it a little bit of dispatchability and the services I'm going to talk about later. So this is why I envision batteries as the perfect, let's say, partner for solar plants among the others. And that's the last direction I would like to talk to you about today. this is what we like to call more grid-friendly solar. And grid-friendly means, in layman terms, how the PV system can be more easily accommodatable to the power system, how it's not going to be a burden to the operator, but it's going to be a source of support during the difficult times. Nowadays, this grid-friendly means two things: provision of a set of ancillary services to the network and operating in grid-forming mode, which I'm going to talk about later. So mainly these two things, and all these two things are based on the capacity of solar to have some power in reserve, to be able to upregulate its output on command. And this is something that solar plants do not have inherently, and you need to see how to provide that either with energy storage and curtailed operation. So this is actually what I'm going to talk about now in more detail. The first thing about grid friendliness is ancillary services. This is really a set of services that traditionally conventional synchronous generators used to provide to this day, of course. But we have tried to kind of isolate them and separate them because new generation sources like wind and solar do not provide them inherently. And we have tried to separate them and say, okay, you need to do that, you need to do the other thing, etc., etc. Here they have been classified into three big categories: voltage stability, frequency stability, and robustness and restoration. This was the separation that came from NHOE grid code. The first class, which is voltage stability, is really reactive power injection mainly, and it is either in normal conditions to support the voltage or during fault in a very fast and rapid manner, and also involves some oscillation stamping. An example here is well known, I think, QV characteristic. So a DER automatically adjusts its reactive power injection or absorption depending on the voltage that can see the terminal. The frequency stability, on the other side, refers to adjustment of real power to the network to support the frequency. This is an example of the PF droop characteristic, where depending on the frequency, the generator may need to adjust its real power. And when the frequency is higher than normal, it is easy actually to decrease your output. But when it is lower than normal, then the system, and the PV in this case, needs to increase its output, which is not straightforward at all, because when it operates at the maximum power point and doesn't have any room for further upregulation, we need to see how this can be done. And lastly, there's this class of services that refers to robustness. Fault right-through, that was probably historically the first service required. Just you need to stay connected to the grid during a disturbance, either voltage or a frequency, because otherwise you will have domino-like cascaded disconnections. Very important, but I think that most plants now, they have a very good performance in that. And then you have also some other emerging services that people are talking about them to start being required by some plants. And this is the black start capability and islanded operation. These both modes require grid forming operation that I'm going to talk about later, and really allows for the PV plant in this case to be able to operate in an islanded mode, to really set up and form a grid around it, and being able to operate in an islanded manner, and at the same time that will allow to contribute to the black start of the power system. Black start is when you have the blackout and everything is switched off, and you gradually trying to re-electrify your network step by step. So these are many services that we would like to see from PV plants to be provided. And now let's talk about this term, grid forming. I've mentioned one source twice. Again, I'm not going too deep into the technical details, but just in an abstract manner, grid following is what we used to have, and it's really a control algorithm that determines how the inverter is going to interact with the power system. So in the grid following, which is the conventional way, the inverter-based resource acts as a current source, as a controllable current source, and this is the current practice. This means that it takes care of the input source of the solar generation very well, because how much solar you have, this is what you inject to the grid. But as a result, it is not very supportive of the grid during disturbances. Okay, and we envision now a transition to the grid forming. Grid forming mainly is a change in the control of the inverter. Of course, it requires some additional hardware capacity, but Generally, the big idea here is that the inverter-based resource operates as a voltage source in the network. And being a voltage source, it means that, it does not directly inject power to the grid, but that the grid draws power from it. It's much more like a synchronous generator operation. And this is why it is much more supportive of the grid disturbances. It can enhance the grid strength, the local grid strength. It can also provide some inertia-like behavior on its own, but it has many challenges when it comes to implementation, especially when the primary source, like here solar, it doesn't have any headroom for power. So this brings us to the next point of discussion. This is where we set power reserves. This really means that the PV systems, to provide all these ancillary services, some of these ancillary services and grid forming, they need to be able to both upregulate and deregulate their output on command and very quickly. That's the basic point here. And because normally they can decrease their output, but they cannot increase it when they're getting the maximum they can, we need to see how this can happen. And this can happen with two ways mainly. In our investigation, there's the batteries aspect, where you install a few batteries and get the maximum power from the PV system. You provide whatever you like to the grid, and you store some surplus to the batteries, and this can be provided afterwards. So this is one way, and obvious, I would say. But there's also this second approach that has attracted the attention of the community lately, even though still it's a debatable idea. This is to keep some power headroom by curtailing power. And the concept here is that even though you have the power, you just don't extract all the power from the PV system. Let's say you extract the 90% deliberately, and you provide that to the grid. So the remaining portion remains there to be either lost, in the sense that you don't extract it, or it can be immediately deployed if there's a need. So in that sense, what you do is really underutilize the installed PV capacity. This is not very different from a conventional generator where you have it operating at 90% or 80% of its capacity during normal time. And this is perfectly acceptable at that time. You underutilize your capacity. But in a conventional generator, you also don't burn any fuel. So you think that you don't lose out anything. Here in the solar, you have a free fuel, which is the solar generation. And when you lose it, it's lost revenues. So this idea is still under debate, and it requires, of course, an appropriate market mechanism if it is to be implemented. But I'm just mentioning it because I feel that it's quite interesting. It's an easy method to convert either existing plants to controllable, dispatchable, semi-dispatchable power stations without big investments or big changes into the hardware and stuff, mainly some control firmware update. But there's a lot of work to be done in the market commercialization mechanism here. Okay. And I think that this is the last technical slide. We have tried here again to summarize some of the important things in the UK and India, and some which are particularly important in the UK or India, and how they relate to the big challenges we're facing. For example, definitely we need more flexible generation. I've mentioned the flexibility many times, and hydro is a very good idea, and gas also is something that we can see in many countries around the world are looking at for a flexible fuel over coal. Okay, so this over coal, and I'm saying over coal because the UK it has a plan to phase out completely coal by 2025, and it's going well, and at the same time increasing their connections. And so this is for the UK, but for India, one important consideration is that still the electricity market is developing and evolving, and we should do that even faster to facilitate this transition. And also there is high potential for hydro plants to be converted to pumped hydro, so as an energy storage. What else? Let's say a few things about stability. So making the PV plants more grid-friendly is important, and the more ancillary services you manage to integrate, the better. And grid forming operation. In the UK, we expect also to see a lot of battery storage and electric vehicles because from 2030, new fossil fuel-based cars will be banned in the UK. So we'll have a lot of electric vehicles in the coming decades. And we need to leverage this new form of energy resource in the network. In India, one big concern is the regional grid strength, and we need to see how we can strengthen it. And here, one idea, apart from the conventional, invest more into the network itself, is the grid forming operation of embedded generation can be very supported because it has been proven that it can increase the regional grid strength. So a mode where islanding and the islanding operation is appropriate and grid forming operation is available in solar, maybe that is a way forward where it can strike a balance between the investment and the grid strength you need to have in the regional grid. So yeah, okay, let's end up this presentation here because I have approximately 50 minutes. Thank you very much for your attention and this invitation. If you would like to know more about this white paper, please you can scan this QR code or can just visit directly this web link. It is freely available. So yeah, that's all. Floor open for questions.
Okay, thank you, Dr. Batzelis. It was a quite interesting informative session. So we have few questions from the audience. First question is, what is the role of inertia or impact of inertia in a microgrid while all sources are powertronic based sources?
Well, the inertia, okay, this is a good question because if we term inertia the way we used to define it in the past, like that comes from the rotating masses, it may be seem irrelevant, but that is one aspect of it. That is one side of the coin. The other aspect is we need someone to safeguard the frequency. Okay, and we cannot leave the frequency from 50 hertz, for example, we have in India, to vary to 40 hertz or 60 hertz uncontrollably, because there's lots of equipment that will not work. So we need to keep it within a particular range. Therefore, we need someone to act like inertia. And in inverter-based generation, as my friend colleague mentioned, we have something that is called synthetic inertia, which we try to emulate the inertial response. But this is not really the solution because that requires already existing inertia there to function. Now, the solution to that, based on recent reports, is the grid forming, because grid forming is what people refer to as electrical inertia, or some other refer to it as damping frequency property. We're still looking at it, but grid forming is we have the source as a voltage source, which means that immediately provides power to the load. It's rather the load asking power from it rather than the PV deciding whether to give it or not. So in that regards, we have something that's going to substitute the term of mechanical inertia in the form of electrical inertia. So I hope that this answers the question.
Yeah, thank you. So the next question we are having is, can residential customers participate in demand responses as a balancing service to manage the uncertainty of solar power generation?
Demand response in balancing service? Well, definitely. This aligns with the direction number 2, which is the demand side response. So this is something that definitely we can and we need to do. But even though technically it's very easy, technically speaking, it's easy to implement that. You can have even in your home an application in your phone or a panel where you can see the prices. You can decide whenever you're going to adjust your load consumption. It is behaviorally difficult because when you have learned to have a luxury of electricity throughout the day without keeping in mind when to use it, it's difficult to change this mindset. And I would like to mention here something that there is this recent project that we have started. This is actually an EU-India, again, Horizon project that we got recently, and that will have some pilots in some parts in India and some villages which are isolated and or have a weak grid connection. So there, we're going to be looking at whether we can adjust the consumers' consumption and the patterns, not only motivated by the price and money, but also by the energy availability. Okay, so this is the whole idea, how people are going to be incentivized more to adjust that. I think that only money is not the solution. We need to start looking at things like environmental impact, like energy availability, and other things in order to make that happen.
Okay, thanks for the answer. Just two more questions we will have. Next question is, in context of the United Kingdom, are there some important policies and regulations imposed by regulator OFGEM like mini grid policy or rural electrification policy, which helps promote mini grid installations?
Grid installations in particular. I'm not sure that we have something like that, to be honest with you. For mini grid, I don't think generally in the UK we don't have too many mini grids off grid installations. We have mini and micro grids which are really not connected. And what I can say that is that National Grid has, you may know National Grid UK, it has a website with many policies and plans and targets and reports. So they are outlining that they envision in the future to see the entire power system as a cluster of many microgrids, interconnected microgrids. No, they call it more of energy island in the sense that there are clusters and clusters of the network that they can operate semi-autonomously for some time. And this again relates with the services and the grid forming we mentioned. So there is a plan for that to happen, but we are not focusing too much on mini grids because we don't have too many mini grids here.
Okay, so I think it was more on the construct of Indian grids because we have few mini grids over here now coming up.
Yeah.
Next question is in smart grid context, we talk about virtual synchronous generator. The idea is to use swing equation in a closed loop control for power converter. Can they recover system inertia loss if adopted widely? Is it the same thing as grid forming as you mentioned in your slide?
Right.
I think
right.
they are asking about recovering
Yeah.
system inertia.
Yeah. Okay, let's get back to that. So I know that, yes, so it is the same thing, but it is better. Grid forming is better. So, okay, because the community are still looking at it, they initially started referring to it as visual synchronous generator because we started trying to have the inverter behaving exactly like the machine. Okay, exactly like the machine, but with different constants. And that's how it started. And it became VSM, visual synchronous machine, or VSG. Now people are talking about the grid forming, which grid forming is like a bigger cluster that big grid forming can be VSM, but it can be also different types of controls. And the idea is similar, that you act as a machine in the sense that you can form a grid, you can act as a voltage source, but it is not entirely necessary to use the swing equation for the power converter. The fact that we had the machine operating this way is because it was related with its hardware and the physics. But now that we have a power source that will be fully controllable, almost fully controllable, we can make it whatever we want. So that's something we need to keep in mind as researchers. We don't have to really mimic the machine. We can make something better. Okay, and in that regard, yes, that can cover up for the system inertia which is lost. It does not have to be related to the inertia constant in the way you know in the machines, but it can be another equation or another control method that can provide a lot of energy instantaneously to the power system when the power balance changes. And when this happens automatically, it acts as an inertia.
Okay, thanks for the answer, Stratis. Last question we'll have as we are running out of time. What does grid code harmonization mean?
Also a very good question, because maybe I mentioned it very quickly. So grid code harmonization is really taking the grid codes of different countries, let's say the UK, India, EU, China, all the countries that start developing their own grid codes, and making them the same thing. It's like coming up with a global, let's say, globally adopted grid code that would have a set of requirements and guidance, and they will be the same across the globe. This is the whole idea of harmonization. Or if not entirely the same, the differences will be fewer. The gain from this harmonization is that when the project developers develop the installations of these systems and they gain some experience, this is transferable from one country to another. And then when the inverter manufacturers, they build their inverters and they need to come up with all these settings and protection settings and operations, they will be the same in many countries, which means that it is easier to build them, not only because you program different functions, but you need to test these different functions, right? You need to pilot. So imagine if you need to change all the settings and all the operations in every country. So the same company, it is not easy to, it needs much more R&D development to do that. Therefore, holistically, this is going to reduce the technology costs, how expensive it is really to build a solar plant eventually. So that's why grid harmonization is important.
Okay, thank you, Dr. Stratis. Actually, we are having more questions, but I think we are right to the end of schedule. So I would urge all the participants that they can directly mail to us or they can contact Dr. Stratis also regarding the same. And as Dr. Stratis have mentioned in the beginning of the slide that they are doing a wonderful work in UK-India Joint Virtual Clean Energy Center. So you can also visit over there. And personally, I also follow some of Dr. Stratis' work on PV integration. So you can also give a look into that. So I want to thank Dr. Stratis for this wonderful session. This was very, very informative as well as interesting. And we came to know about very wide aspects of upcoming limitation, challenges, barrier regarding to solar PV systems. So with this, I would like to present the token of thanks to Dr. Stratis. So thank you, Dr. Stratis, for accepting our invitation. And we hope that we will again connect and both United Kingdom and India together will work for a better future grid and we'll set milestones for time to come. Okay, Stratis, thank you very much.
Thank you, Arindam, and
Have a nice day.
Thank you very much, and yeah, okay, keep in touch. Bye-bye.
Bye-bye. Thanks. Hello, participants. Actually, we are going to start the next session. So this session will be on IEEE. So we are going to share some interesting information regarding IEEE. And good thing is that we have some coupon codes as well, which will be very, very helpful to different participants, which they can use and become a valued member of IEEE, which has various benefits to it. So for this, we have the title of this session is Introduction to IEEE and IEEE UP section. And this session will be presented by Mr. Ankit Yadav, who is a PhD scholar in IIT Kanpur. Ankit Yadav is a PhD scholar in IIT Kanpur, India. He has received his BTech in electrical engineering from KNDG Modi Engineering College, Uttar Pradesh Technical University, and MTech in power engineering from Delhi Technology University in 2011 and 2014 respectively. Ankit is actively involved in various IEEE activities. Currently, he holds the position of student branch chapter, and student branch AG, operation and coordination, subcommittee of IEEE UP sections. Section student representative of IEEE UP section chairperson, IEEE PE student branch chapter, IIT Kanpur. He was also IEEE PhD ambassador, section 2020. Apart from this, Mr. Yadav has received several accolades from IEEE, including the Outstanding Student Volunteer Award for the from the IEEE India Council in 2019 and the IEEE Outstanding Student Volunteer Award from UP section in 2020. His area of interest includes HVDC, power converters, application of power electronics in power system. So with this, I would like to Mr. Ankit Yadav to please take the stage and present to us the importance and benefits of becoming a valued member of IEEE. Thank you.
Thank you, Arindam. Please give me the share access so that I can share my presentation. So I hope my screen is visible to everyone.
Yeah, Ankit, it's visible. Thank you.
So welcome participants. Welcome to the today's talk on IEEE. So I will be giving just a brief about the IEEE and its introduction about the IEEE system. So not taking much of your time since we are already have a smaller schedule. Let's move ahead. So the IEEE is basically the world's largest professional association. It is dedicated to advancing technology, innovation, and excellence for the benefits of humanity. And since all of among the participants, many of you are already IEEE members, so you are already aware about a lot of things. So I will be focusing upon the some selected points only. So if you see the roots of IEEE, it basically a combination of two societies. Earlier there were one Society American Institute of Electrical Engineers, and there was another society, Institute of Radio Engineers. So they both of the societies combined, and they form a single unit that is called IEEE, and it was done on the 1963. So coming ahead, this is the current reach of IEEE. We have a total 10 regions covering all the globe, and our region that in which we belong, India and other neighboring countries, we are basically part of IEEE 10. And then if you see the global reach of IEEE, so we have more than 420,000 members, 39 technical societies, in around 160 countries, 1,800 annual conferences, some 4 million technical documents, and so that. This is a rough structure of IEEE, that how the IEEE looks, and it is not the exact representation, but you can get the idea that how the hierarchy goes. IEEE is basically divided into 3 primary parts. One is based on geography, and second is the societies, and third is the affinity and special groups. And then if you come to geographical distribution again, then the entire IEEE is divided into 10 regions, which are again divided into sections, and these sections are divided into student branches. In terms of technical breadth, it is divided into 39 societies, and considering the special interest, it is divided into affinity groups and professional and WIE and other special groups. So then coming to next, when you become a member of IEEE, basically you become a member of your, if you are a student, you will become a member of your student branch. If you are a professional, then you will become the member of your section. And by being a member of branch, you by default become a member of section, and you can get all the benefits that a branch that IEEE provides to your branch, your section. And apart from that, you can also take some add-on. There are 39 societies for you to choose. This is basically a kind of pizza. IEEE is the pizza, and the societies are toppings on it. So it's up to you what is your taste and what is your interest. You can select the relevant toppings on your IEEE pizza. Now these are the special interest group, and that is basically women in engineering and professional that comes along with the IEEE. And the interesting thing is that this young professional and women in engineering is free of cost. So if you are an IEEE member, you can get these societies just by registering to it and without paying any fee. Now, when it's come to IEEE UP section, basically our section was formed in 1992. Before that, we were basically a subsection of Delhi section. And if you see the brief of our section, in a section we have 95 branches, 28 affinity groups, then 14 section chapters. We have 108 student chapters. We have 9 side groups, 2 section affinity groups, and around more than 3,000 active members, more than 1,500 student members, like that. So now comes the main focus of this presentation, the primary part, the membership benefit. So IEEE gives you an opportunity to stay technically current. It gives you opportunity of professional networking, helps you in developing your career, helps you in continuing your education, helps you in getting the membership of other societies and other documents at a reduced cost. Then of course the awards and recognition. So to keep you technically active, technically current, it gives you a subscription of a Spectrum, subscription of Institute magazines, and I can tell you from my experience, the Spectrum is quite wonderful magazine, and it is also have a dedicated website. If you can visit this website, it is continuously getting updated with the new kind of ideas, and that has the if you see as a researcher, we are continuously focused on the research part, the technical part. That is quite good, but if you see how that impacts to the real life, how our research is impacting to the real life, what the products are being developed, what are the new ideas being created, then please visit the Spectrum website, and you will get the quite wonderful information there. Then of course you are already aware about the Explore, the Willy, the IEEE events and conferences, the events like this that you get to attend with your IEEE membership. Comes to the professional networking, it gives you basically a Google apps that you can use. It gives you IEEE areas that can use, and it has a quite huge impact. So when you are mailing to someone, if you are mailing with an email ID that is having IEEE.org domain, then that the recipient gives some privilege to this, and he will not ignore it. Let's say straightforward. Then of course you can get connected to membership network, and you can get to attend the local meetings, and you can volunteer like those things. When it comes to career development, it has a job site, websites, then career alert option. It has a mentoring option by IEEE Collaboratech, where you can get a member get a person to mentor you from anywhere around the globe. It helps you in preparing your resume, and then of course give the awards as well. For continuing education, there are a lot of options, but of course, since we are deep into the research and we are utilizing the IEEE for a longer period, so everyone is aware about these benefits. So I won't be discussing it. Now comes the reduced membership fees. So with the IEEE membership, you get the options. You get the options to purchase other IEEE products at the reduced rate. Let's say if you go to the IEEE resource center, then there are multiple videos, multiple lectures that are already recorded, and that you can get at a reduced cost. Then of course you get reduced price for the conferences, publications like this Para 21 event. If you, since you have registered, you must have seen the different rate that were applied to different kind of members. So with IEEE membership, you get that benefit as well. Now the thing you might have been waiting for, the coupon codes. So if you are looking to join IEEE or to renew your membership, these are the coupon codes currently active. The Future 50 is basically for the student members and graduate student members. By applying, basically the student membership fees is up $27, and with this coupon you will get the rebate of 50%, and it is active throughout the year. So if you are taking a membership now, you will get this. You can apply this coupon and can get the benefit of it, and it is applicable for renewable as well. Now comes to the professional member part. So there are basically two coupons available, that is IEEE Day 21 and IEEE Day 21R. So first one is for the renewable and for joining in the new members, and it is valid for the 3rd October to 9th October, the coming month. And the second one is basically to reinstate the membership of professional members. Again, it is valid from 1st October to 9th October, and they both are giving you a rebate of $30. If you are taking a society membership, especially PS Society, then again for PS Society we have a coupon code of Future 50 PS, and that is giving a 50% rebate to the student members. And apart from these, I have just shown you these four because I thought that these are relevant here. But if you are having a society membership of some other societies, then search on Google. There are multiple membership are coming now, and especially on the occasion of IEEE Day, that is on the 5th October. There could be multiple coupons available, which would be basically if you can say valid for this IEEE Day time period only for 1 week or 2 weeks. So if you are interested in renewing or taking a membership, please, this is the right time, and visit those websites and see the coupons available. Now these are the multiple awards that IEEE provides. You can go through multiple websites like Region 10 website, the section website, the IEEE website, the IEEE student website, and you can find about all these awards that are being given continuously. And if you are thinking about to apply for some award, I encourage you to go ahead because if you apply for the award, then only there is a probability that you can get it. And since there are multiple criteria with which the many members who have already got the award, they are not eligible for the next award. So there might be that possibility that if you are thinking that I am not the good enough as per the others, as equivalent to others, Then there is also a possibility there's all those others whom you are thinking are good enough, they have already received the award. So it might be your chance to get the award. So please go ahead and explore this. Then comes the awards from the section. So section has just floated a call for nomination for IEEE UP section award. So for the members of UP section, if you are interested in the awards and you want to apply, you are willing to apply, then check your e-notice. You must check your mailbox. You must have received your e-notice from the section, and you can get the deadlines there. Then these are the multiple initiatives that has been taken for the students for their benefit. So section basically gives the rebate on conference registration. It provides student travel support, industry internship programs. Then it does the IEEE webinar and seminar series. It does a graduate talk series that is for the graduates. There are multiple volunteer training sessions, conferences, pre-university activities, financial support for the activities, like those. I mean, I will share this PPT and you can go through this and see it. Then there is a website that is IEEE Global Benefit Finder. You can go it and see what benefit you are looking for, and you can get it. Apart from that, I will also recommend everyone to have an account on IEEE Collaboratech. There you will, IEEE Collaboratech is basically a social media of IEEE. The advantage is that it is a purely group of technical members like you. It is a group of IEEE members, and then there are multiple technical discussion group, multiple social interest groups that you can join. You can follow multiple societies. You can get the updates there. So there is a lot to explore on IEEE Collaboratech. There is a lot of benefit. If you are looking for a job, you can use Collaboratech. If you are looking for a mentorship, you can go to Collaboratech. So if you want to get benefited from IEEE membership, you need to start exploring, and the way to start is to go to IEEE websites, go to IEEE Collaboratech, go to IEEE Spectrum. Then these are the few important links that I have mentioned here. So I'm not giving you the link, I'm giving you the headings, and if you put these on Google, you will get the links by default. So basically the IEEE website, the IEEE student website, the members websites, the section website, site website, YP, WIE, VTool, IEEE standards. So you can join the standard association as well. IEEE education resource. So this is the place where you can get the video lectures, recordings of the events at the reduced prices. Then humanitarian and other activities, conferences, publications, societies, all those. So those who are interested in getting connected, we have these groups with us that you can follow. For the section members, we have a section WhatsApp group, a section Telegram group. We have a dedicated group for the section office bearers, I mean the branch office bearers of the section. Then we are also present on Facebook. You can follow us there. You can get any details, get the alert for the activities. We are available on the LinkedIn and of course other website and newsletter as well. So that's all. Thank you. This is a IEEE TV that you can explore. Get connected with IEEE. It is available on LinkedIn and other things. So that's all. Thank you. If anyone has any question, please.
Participants can ask their questions regarding IEEE. So they should really take the benefit of this.
So time was short, so I tried to cover maximum thing as soon as possible. I will share this PPT with you and you can see it. But if you have any query regarding IEEE, please go ahead and ask. I think no one has any doubt. Okay, someone has something. Someone is asking, I am IEEE UP section member. How can I become a PS member? So first thing is that go to IEEE PS. It is not about PS. It is about any other societies as well. So if you want to become PS member, if you want to become YP member, if you want to become WIE member or any other society member, go to that society website. On that, you will find the link join now. click on that link. It will take you to the IEEE member and subscription website. There it will ask you your IEEE login details, and all those things you can, all the society membership you can check from there. So of course you will need to do the payment and other things similar to the process that is followed by IEEE. That is one way. Second way is that if you remember, when did you take the IEEE membership? You had basically opened one portal. Go to the same portal and it has an option of IEEE societies. Go to that society and there you can select the societies you want to take. So it doesn't matter which path you follow, it will always bring you to the same website that you have used for your IEEE membership. So and from there it will proceed for the payment and checkout process. When can we renew my membership? Okay, so what happens that with IEEE, the renewal process starts from August onwards. So from 15 August onwards, the renewal process has started, and for the membership, new membership is also being given. So if you are interested in taking the membership or renewing membership, you can start the process anytime after the 15 August, and it would be valid for the next year as well. So if you renew your membership today, it would be valid for the December 2022.
So I think one participant also asked that to share the group ID to join.
Yeah, I saw that, and I will share the group ID of WhatsApp as well as Telegram group. However, I personally recommend everyone to follow the Telegram because that has a limited membership. I mean, a huge number of people can subscribe that, and the message being forwarded to Telegram and the WhatsApp group are identical. So be ensured that the both groups are in sync. So I will share the both groups. It's up to you, but I suggest to take the preference to the Telegram group.
Yes.
We will mail it.
Okay, Ankit, I think we don't have further questions. So I would really urge all the students to take benefit of this, as there are so many benefits to be explored for students at graduate, undergraduate, postgraduate, and all different levels. So there are so many awards we won and so many competitions are there, which can really upgrade your resume and your work profile. So with this, I would like to conclude the session, and I would like to present the token of thanks to Mr. Ankit Yadav for presenting to us the benefits of the different section of IEEE and what are different awards available at IEEE. So thank you, Mr. Yadav, for giving this presentation. So hope we'll getting many new members through this. So
thank you, Arindam, and congratulations to Team Pera. You guys are doing a good job. Thank you.
Thank you, Ankit. So moving on to the next, another important aspect of IEEE is the Power Engineering Society. So this session will be delivered by Mr. Akhilesh Prakash Gupta, and the title of his talk is Introduction to IEEE PES Society. So Akhilesh Prakash Gupta is a PhD scholar at Indian Institute of Technology, Kanpur, India. He has received his BTech in Electrical Engineering from JSS Academy of Technical Education, Noida, and MTech in Power Engineering from NIT Warangal in 2013 and 2015 respectively. His area of interest includes power system dynamics, system equivalencing, wind turbine, and wind power plants. Akhilesh is actively involved in the IEEE activities. Currently, he is a chairperson of IEEE PE student branch, chapter IIT Kanpur. In the past, he has been the vice chair and treasurer of the same unit in 2019 and 20 respectively. Also, he had been the secretary of the IEEE PES UP section chapter for the year 2019. He has delivered few invited lectures and actively involved in organizing many activities, including PERA 18, UP PES IES Congress 2019, and distinguished lecture programs. He has presented the IEEE PES UP section chapter twice in 2019 at the PES India Council meeting and R10 chapter chairs meeting in Bangalore and Macau respectively. So with this, I would like to invite Akhilesh Prakash Gupta to please explain to the audience about the IEEE PES Society. Thank you.
Thank you, Arindam. Am I audible?
Yeah, you're audible and video
Uh,
is also nice.
okay. Thank you, Arindam, for giving a wonderful introduction. So now let me just share my screen. So is my screen visible? Is it in full screen? Uh, hello. Hello, Arindam. My screen is visible or and my audio is clear to
Visible.
you? Okay. Okay. Thank you, Pera team, for giving me an opportunity to present a discourse on IEEE Power and Energy Society. Myself, Akhilesh, as Arindam has already given a brief introduction of myself. So now let's moving further. Just now, my colleague Ankit Yadav has already explained a lot and has given a very brief introduction of IEEE, which is a world largest professional association for advancing technology of humanity. It is having a global reach, as you all know, and it is having a membership of around 4,22,000 members around the world with 160 plus countries. There is a lot of student members also with, I guess, around 25% members are in the student grade. It is also having uh, like a very long or a very wide technical background with more than 4.5 million of technical documents, and there are more than 200 plus top cited periodicals and activist standards. So there are so many technical societies in which the PES is one of the major technical society, and it is also the second largest society. The IEEE is having a social impact with its public policy engagement, global humanitarian effects, and educational and certification, and also the ethics in the technology. As I have already told, the PES is one of the society of the IEEE. The mission of IEEE PES is to be the leading provider of scientific and engineering informations on electric power and energy for the betterment of society and the preferred professional development source for our members. So this is the mission of IEEE, and it is founded in 2008. um, w- Now it is having a membership of around 38,000 plus members. The present president of IEEE PES Society is Jessica J. Bain. There is a PES governing board, which includes vice presidents and other executive committee members. They are having the responsibilities of new initiatives and outreach, membership and image, publication and education. Then there are some technical activities like standing committees, standards, developing and technical committees, coordinating committees. They also do lot of conferences, webinars and meeting across the globe. So there are also like 250 plus chapters, student chapters, and and at the country and the section level also they have a very great representation. So this is what they have the presence. We know IEEE is divided into 10 regions. From region 1 to 7, they are in the North America, and they are 131 PES chapters, then 62 student chapters are there. The region 8 includes the Europe and Africa. There are also so many chapters and the student chapters and with thousands of the members. The chapter 9 is including the countries of South America, and the region 10 includes the countries of Asia, Australia and the New Zealand. We There is one point to be noted that the region 1 to 7 are in the North America, but more than 50% of the members are outside America. That is means like they are having so many regions in the America, but the membership are more, or the number of members are more in other countries. So the PES society is having the members from different utilities and different domain. So there are members from academics, research institutes, manufacturer and the system suppliers. They are also having the members from the government and the regulatory authorities, testing labs, consultings, and many more. So it has a very wide spectrum of the membership in from students to the professionals. The growth of the PA society has been happened very fast since 2007, where it was only 23,000 of the members, while today there are more than 40,000 members. So in the last 10 years, just they got doubled in the terms of membership. The projects which PES is driving, one of the major project is there, IEEE Smart Village. It is a institute-wide humanitarian program supported by the PES. It is also a signature program of the IEEE Foundation, and it has a on objective of providing the electricity to the off-grid remote villages. So where there is a no supply of the power, or where there is a very it's very difficult to get the electricity from the city, there they put the uh, an isolated grid, or with the help of the solar panels, and they provide the lightning load especially to the villagers. So this is what a very good initiative which PES is taking worldwide. Here, the details can be found in the website IEEE The second project is again on the IEEE smart cities. They are focusing on developing a city where all the communication, transportation, building, energy, networking, everything is very smart, and there is a two-way communication. So this is also a very ambitious project which PES is driving, and its more details can be found here in the website smartcities.ieee.org. The another project is on IEEE Smart Grid. Again, they are here for developing a power grid which is very much well equipped with the information technology, artificial intelligence, and the communication in technologies included. So IEEE Smart Grid is another project with PES is driving worldwide, and they are having so many collaborators in this smart grid project. Then IEEE is also very much focused in developing the women in power. As we know already that there is a affinity group within the IEEE, it is the women in power. So sorry, the affinity group in within the IEEE is women in engineering, WIEE affinity affinity group. Same as for the PES society, there is a group for women in power. So PES is fostering a more diverse leadership by supporting the career advancement, networking, and education of the women in the energy industry. PES is also very much focused in mentoring the young professionals. In the PES, there are more than 6,200 PES young professionals worldwide, and it is also growing very steadily, and it helps the young professional to educate and in the upliftment of their career goals. The PES is engaging the academics and the research activities by providing the help in publishing research, sharing ideas with peers, poster presentations, and standard developments. So here there are so many benefits with the PES society, which if you are the member, then you can explore all these research paper, conferences, webinars, which PES is organizing across the world. The PES standard development life cycle. So as we know that in the IEEE there are so many standards, and which are developed by some i- standards committee. So in the case of the power and energy society, there is a one standards committee which takes the responsibility of from developing the standards, its approval, to the maintaining and updation of these standards. Here in the life cycle of the standard is shown here in the right side. You can see from initiating the project, the proposal for the standards goes to the working some for that particular working group. Then the drafting committee drafts the proposal for the standard, and then the balloting of the standard happens, and then after gaining the final approval, the standards get approved and it's added to the IEEE library. Then the PES also takes the responsibility of maintaining and the updating the standards. The complete detail of the standards can be found here in the standards.ieee.org/get involved. So all these informations can be found on these websites. I will share this presentation. You can go through these websites and get more in detail of any specific project or any specific uh, thing which I have discussed right now. You can go get all the details from these links. So as I have told that in the IEEE there is so many technical committees. So same as for the Power and Energy Society, there are 17 technical committees and 3 coordinating committees. So the technical committee includes some like electrical machinery, insulator conductors, nuclear power engineering, power system, communication, dynamics, instrumentation, operation, planning, relaying. So all these are um, having a separate technical committees which have their specific role in their specific domain. So same as there is 3 main coordinating committees. The first one is intelligent grid and emerging technologies. The second one is marine subsystems, and the third one is wind and solar coordinating committee. One thing we can observe here in the IEEE, more than 45% of these standards are created by the Power and Energy Society. So this is a very good achievement which we have obtained, being the second largest society of the IEEE across the globe. So more than 45%, like around 50% of the IEEE standards are created and maintained by the Power and Energy Society. So in order to stay technically proficient with the PES, there are so many benefits which PES members can obtain. Here you can learn new skills and technologies and gain insight from others through conferences, committee participants, webinars, and etc. It provides the cost-effective workforce training. The PES also helps its member by accelerating identification of best practices worldwide. It drives and understands the standards and the key technical issues. The PES also helps in building a network of professionals, colleagues for the fast access, advice, and the problem solving. It helps in gaining and enhancing skill in mentoring, management, and the speaking. So these are the all benefits which as a PES member you can get. Here, there is one important website which PES is providing to us, that is the resource center of IEEE PES. Here the website link is given. This is the resource center. In the resource center, the most extensive library in the world is devoting to the exclusively to the Power and Energy Society. So as a PES member, you, or even if you are not a PES member, you can access the resource library and you can get benefit from the lot many journals, papers, and video tutorials, and so lot of things. The IEEE PES Resource Center is a database that showcase videos, publication, presentation slides from PES conferences as well as webinars, technical reports, tutorials, and more. These materials have been prepared and peer reviewed by the professionals in the field, and they are available to download by IEEE members, and they are also publicly available with most of the content which are freely available to all. So this is one of the very good, and I suggest you all to go to this resource center. Here you can find so many technical as well as non-technical documents. So PES is also involved in organizing so many global conferences, more than 30 conferences per year it organizes. The major conferences are like ISGT, then general meeting. There is an APEC. It happened in Macau in 2019, and then ISGT Asia, Europe, and the North America. So there are so many conferences which PES is organizing. Then there is a publication. There are two magazines, and then there are so many transactions and open access journal. Apart from conferences, you can get your paper or you can get your journal published in these open access journal or the transactions. Now coming to an important part about how to open a student branch chapter. So if you are a student at an institute or the university, you can initiate. If there is no PES chapter, then you can initiate it also, and you can open and get benefit from the PES headquarter directly. So for that, first you need to find out student branch of your university. The process is given here. You can go through this process. Once you get the student branch in your university, then you have to select an advisor. The advisor can be any faculty member of your university or the institute, and if he agrees to be the advisor, then his IEEE details are required there. After, at the fourth step, you have to submit a petition. The petition can be obtained from the website, which I have shown before. The petition form can be filled here. The required details are like proposed name of the student branch chapter, your IEEE member number, name and email address of the other members, and there is a requirement of like at least 6 IEEE members, which should be there in the starting of the IEEE student branch chapter. So now the petition can be filled and submitted. After submitting the petition, it goes to the IEEE member and geographical activities for the approval. Once it got approved, you will get the approval mail, and for any queries you can mail it to the petition at IEEE.org for any questions or the doubts if you are having. So once it get approved, your student branch chapter is now active. You can start organizing and hosting activities, and you can report it on the IEEE vTool website, and you can get the benefits which IEEE PA society directly gives to the student branch chapter. So the opportunities, this is an important point here. High performing student branch chapter program is there, then the distinguished lecture program is there, then there are so many awards like outstanding chapter award, high performance chapter award, membership contest, website contest. So all these awards are can be hosted by your student branch chapter or the section chapter, and you can get benefit of these awards which IEEE which PES headquarter gives, and here you can directly get the benefit of from these awards. So other benefits like development of the network with the PES colleague, providing a quality technical activities, and providing the leadership development opportunities you will get from once you open your chapter, your student chapter or the section chapter. Now there is an announcement of IEEE PES UP section chapter that it has uh, accepting the application for the outstanding engineer award. So if your affiliation is UP section, or if you are affiliated to a UP section, then you can apply for this award. Here you have to just mail your CV with the details or with the letter from the nominator to this mail ID, and this application is open till 30th of the September. Eligibility is there that you have to be affiliated to any institute or the organization within the geographical area of the Uttar Pradesh section. The past winners of this award here you can see in the 2016, the Professor Sakat Chakravarti from IIT Kanpur, then Professor R.K. Singh from MNIT Allahabad, and then Professor N.P. Padi from IIT Roorkee. They have already received the award. So if you are also eligible and if you are interested, you can apply for this award. So this is the announcement from UP section PES chapter. So this is all from my side. I hope you have got some useful information regarding the IEEE PES Society. If you want to know any further details regarding the IEEE, you can go to this website ieeepes.org anytime, and you can also post your queries to us directly. We will be very readily to we will be very happy to help you out in any such queries. So over to you, Arindam. That's all from my side.
Okay, thank you, Akhilesh, for the nice presentation.
Yes.
So I hope this will be really beneficial for all, and I would urge that everyone should take benefit of Peace Society, because being an electrical engineering graduate, whatever research we do, mostly there are many journals, power systems, smart grid, they all belong to this PS group. So students should really take the benefits from this. So with this, I would like to invite questions, if there are any, from the students. So Akhilesh, one question I will
Yes.
simply ask. So
Yes.
like, if one is already an IEEE member,
Mhm.
so does he have to, for becoming member PES, does he have to apply separately or what?
Actually, taking the membership of the IEEE and the other societies are completely separate process. But you can, while renewing or while taking the first time your IEEE membership, you can add the PES membership also in your card, and you can check out at the same time. So, but the condition is that to get the PS member, you have to be the IEEE member also. So the simultaneously you can take the both membership, or first you can take the IEEE membership and then the PES membership. But the opposite is not possible. Like you cannot take the PES membership without having the IEEE membership. In some cases it is possible, but I don't suggest you to go for that because it's very expensive.
Akhilesh, just
uh,
pardon for this interruption.
yes, yes,
Actually,
yes.
there is a concept of associate membership as well.
Hmm.
Though the utilization, I mean, if you say in entire UP system, there are only 5 or 6 members who are using it. So
Hmm.
whoever interested can explore that part also. So
Okay, yes.
in that part, you would not have to take the membership of IEEE, but you can become a membership of IEEE by taking the membership of some other society. But that is quite costly.
Yes, yes, that's what that's what my suggestion is. Better not to go without having the IEEE membership just for the PS membership. It becomes very costly. Hmm. So if participants are having any further questions, they can ask, or they can ask us directly to our mail ID anytime. If they get some doubts, we'll reply them on their like on the mails also.
Yeah, it will save much time from the participant side also. So they can get tailor-made things from our
Mm.
speaker. So is there any more questions? I think there is no further questions. So I think
Mm.
that presentation was quite nice. So I
Thank
think
you.
most of their doubts has been already being covered in the presentation itself.
Mm.
So with this, I would like to conclude this session. So I would like to thanks Mr. Akhilesh Prakash Gupta for giving us his time and presenting this talk on PS Society. So I would like to, from the on behalf of Pera team, I would like to give you a token of appreciation for being here with us and presenting your talk.
Thank
So
you.
thank you,
Thank you.
Akhilesh, for
Mm.
your wonderful talk, and have a nice day ahead. Thank you. So this is simply the tomorrow's about tomorrow's session. So the participants have already the timetable with them. So tomorrow we will have Professor Mukesh Nagpal with us, and he will be delivering his talk on protection solution of distributed energy resources and micro operation at 9 a.m. So we will be eagerly waiting for you all, and have a nice day. Thank you.